Hi, welcome to BC Video 6.1 Part 1, Introduction to Euler's Method. Okay, 6.1 has slope fields, which we saw last year, but the main thing is it has Euler's method on page 410. So Euler's method is a way to approximate, emphasis on approximate, these are not exact answers, to find the value of y equals c. Now they're going to call the function y of x instead of f of x, where c is a constant. And here's what they're going to give you. They're going to give you a differential equation, dy dx equals a function of x and or y. So it might be dy dx equals 3x squared, might be dy dx equals y cubed, might be dy dx equals x squared plus y. They'll also give you, sometimes indirectly, a small value for h, which is your delta x, and they'll give you an initial condition x0, y0, which means that is a point on the solution. So note, when are we going to use Euler's method? Usually it's when the differential equation is either impossible or too difficult to solve, or if they tell you to use Euler's method. Okay, so here's an example. They're going to give you dy dx equals x plus y, so they're going to give you a differential equation. This time it has x and y. They're going to give you an h of 0.2, and they're going to give you an initial condition of y of 0 equals 1. So they're basically telling you the 0.01 is on the solution to this differential equation. Remember, the solution of a differential equation is y equals. So we have 1 point on our solution, and we want to find an approximate value, let's say, of y of 2. So we've got to get from 0, x equals 0, to x equals 2, and we're going to do it in increments of 0.2. All right, so here's how it works. You have this mystery function y of x that we're looking for, but we do have an initial condition. We do have a point on that curve, okay? That's the same thing, nothing different, and here's how it works. So I have my curve y equals f of x. Let's say this is my actual y of x curve that I wish I could find the solution for, but I can't, okay? So what I'm going to do is I'm going to start at that first initial condition, that first point. Now, I'm making my h very big so you can see, but actually h is going to be tiny, like 0.1, 0.001. So you can see everything, I'm going to make my h kind of big. So what happens is, at that point, I know what the slope of the tangent line is, because dy dx is actually the slope of the tangent line. So what happens is, I will be able to draw a slope. I know what the slope of the tangent line is at x0, y0, because they're going to give me a formula for the slope. And I'll be able to draw that slope, and I'll draw it as far to the right as h goes, from x0 to x1. Now what happens is, the actual value on the curve that the solution curve is x1 comma y of x1, but I'm getting this point up here. Now, of course, it's the reason it's so far away is because my h is big. You can imagine if my h was tiny, you can see the red curve and the purple curve here are almost at the same height. So what it is this is x0, y0, this is x1 comma y of x1, but I don't know what that value is. I'm approximating that height with this height right here, which I'm going to call, it's still x1, but I'm calling it y1. So what is my height y1 actually equal to? My height y1 is the height of y0, so it's this height here, plus this height right here. Now, what I'm going to do is I'm going to call that height, that big whole height is y1, this height y1 minus y0. I'm going to call that delta y. Now, this is where it gets a little weird. Delta y, you should agree, is the same thing as delta y over h times h. But my h is actually delta x. So my delta y over delta x is actually my slope. And my slope is f of, in this particular case, f of x0, y0. So my y1 value is my y0 value, which I was given, plus the slope, f of x0, y0, the slope here, times whatever my h is, which is this little number that you'll be given. Okay? All right, so again, they're going to give you a differential equation. They're going to give you an initial condition. They're going to give you a value of h, and they're going to ask you to find f of something or other. Okay? So just as an example, if you did have y minus x as your differential equation, then the slope of the tangent line at the, let's say, initial condition 0, 2 would be 2 minus 0, the y-coordinate minus the x-coordinate. So that would be x equals 2. Now that's going to repeat itself, just like up here we had y1 equals y0 plus f of x0, y0 times h. y2 will be y1 plus f of x1, y1 times h. And that's a recursive formula. So again, you're going to be given a differential equation, an initial condition, and a value for h. You'll be asked to approximate y of a number, y being the solution to this differential equation. The formula we're going to use for Euler's method, and this is the formula you want to memorize, is that yn plus 1 is equal to yn plus h times f of x n yn. So, a few iterations, y1 is equal to y0 plus h times f of x0 y0. y2 equals y1 plus h times f of x1 y1, y3 equals y2 plus h times f of x2 y2. So here's an example all worked out. So here's our differential equation, here's our initial condition, here's our h, and here's what we've been asked to find. Okay? So we have our initial condition, the point 0, 1, that's our x0, y0. So what we do is we make a table so we know which iteration we're at. At n equals 0, we have our initial condition, our point 0, 1. x0 is 0, y0 is 1. Now, to find y1, y1 is y0 plus h times f of x0, y0. Well, y0 is 1, h1 is 0.1. f of x0, y0, well, x0 is 0, y0 is 1, and f of xy is x minus y. So that's going to be 0 minus 1. And then you simplify that, you find out that y1 is 9. And then you start the process all over again. Now, as far as the x column, remember what we're doing is our h is 0.1. That's our delta x value. So as far as our x column, that's pretty straightforward. We're starting at 0, and we're just going to add 0.1 every time. And you're going to do that until you get to 0.5, because that's what you want. The answer right here is the answer we're looking for. Okay, so that was y1. So now we're going to find y2. y2 will be y1 plus h times f of x1, y1. Well, y1 is 0.9. Our h is that constant up here. Our h is 0.1. And then f of x1, y1. Well, x1 is 0.1 and y1 is 0.9. Remember, our f of xy here is x minus y. So that's going to be 0.1 minus 0.9, which is negative 0.8. Multiply that by positive 0.01. That'll give 0.08. 0.9 minus 0.08 is 0.82. And that'll give me this number. Now you can see this is a very tedious method. So very often they'll only have you go 2 iterations and stop, because by hand without a calculator this would take forever. And then you'll do it again. y3 will be y2 plus h times f of x2 y2. That'll be 0.762. And then you'll keep going y4, and finally you'll get y5.